Welcome to the NPTEL MOOC on Discrete Mathematics. This is the first lecture on number theory. In number theory, we study the theory on integers. Integers along with the two operators multiplication and addition and the two constants 0 and 1, you would see in the module on algebraic structures that forms what is called an integral domain. So, number theory is the study of this integral domain. So, in number theory, we deal with the set of integers. And the operators multiplication and addition along with 0 and 1. Together these form an integral domain. For two integers a and b, where a is not equal to 0, we say that a divides b. If there exists an integer x so that b equals ax, that is, upon multiplying a with some integer x, we would get b. That is when we say that a divides b, and this is denoted in this fashion using a vertical bar. This notation asserts that a divides b. The negation of this, that is, the negation of a divides b, is often written like this, with a cross across the vertical bar to indicate that a does not divide b. So, let us see some results related to division. If a divides b, then for every c which is an integer, it is the case that a divides bc. This is easy to show. If a divides b, then b equal to ax for some integer x, then for any c, we have b equal to ax. Therefore, bc equal to ax into c, which by associativity of multiplication can be written as xc times a. This implies that a divides bc. So, that was easy to show. Another result is this: if a divides b and b divides c, then a divides c. In other words, the divides relation is transitive. This is also easy to show. A divides b implies that for some integer x, b equal to ax. Similarly, b divides c implies that for some integer y, c equal to by. Therefore, c can be written as the product of xy and a, which means there is an integer, so that a into that integer is c. So, that implies that a divides c. The third result is this: if a divides b and a divides c, then for any pq that are integers, a divides bp plus cq. That is, if a divides b and a divides c, then A will divide any linear combination of B and C where the linear combination has integer coefficients. P and Q are the coefficients of the linear combination, these are integers. So, any such linear combination of B and C will be divided by A. How do we show this? What is given is this: A divides B and A divides C. If this is the case, then by the definition we know that there are integers x and y, so that B equal to Ax and C equal to Ay. B is a multiple of A and C is also a multiple of A. In that case, for any xy, we can say for every pq, which are also integers, bp plus cq is A into px plus yq. For any pair of integers p and q, we can write bp plus cq as apx plus ayq, because b is ax and c is ay, which implies that for all integers p and q, there exists x and y such that bp plus cq equals A into xp plus yq. That is because this statement is a weaker statement in comparison to the one above. Or in other words, for every pair of integers p and q, bp plus cq is az for some integer z. In other words, for all pq which are integers, bp plus cq is a multiple of A, or A divides bp plus cq, and that is precisely what we wanted to show. For any pair of integers p and q, the linear combination of b and c is a multiple of A. A fourth statement is this: if A divides B and B divides A, then A equals plus or minus B. If A divides B, then A into x is B for some x which is an integer, and if B divides A, then By is A for some integer y, then Axy is By, which is A, where both x and y are integers. So, there exist integers x and y, so that Axy equal to A, or in other words xy equals 1. If for integers x and y, x into y happens to be 1, then we have only two possibilities: either x equal to 1 and y equal to 1, or x equal to minus 1 and y equal to minus 1. In the first case, we have A equal to B. In the second case, we have A equal to minus B. So, combining these two, we can assert that A is plus or minus B. If A divides B for positive A and B, then A less than or equal to B. Prove this yourself. And another property of the divides relation is this: if an integer x, that is non-zero, is given and A divides B, then xa divides xb. This also you can try yourself. So those were some results about the divisibility relation. Now let us see what is called the division algorithm. At the heart of this algorithm, we have this theorem. For any two integers a and b, where a is greater than 0, b need not be greater than 0, there exist unique integers q and r such that b is qa plus r, where 0 is less than or equal to r, which is less than a. So when you find such a unique ordered pair QR, Q is called the quotient and R is called the remainder. So how do we prove that there exists such a unique pair QR? That is what we want. We consider the real line. On this real line, consider point B. B is an integer, it may be positive or negative, and we have a which is greater than 0. From B, let us start marking points that are at distance a. So we get an arithmetic progression. B plus a is the next point, b plus 2a is the one after that, b plus 3a is the one after that, and so on. That is going to the right side. If you go to the left side, we have b minus a, b minus 2a, b minus 3a, and so on. So starting from B, we are going to the right, jumping at a distance of a every time. Similarly, we can also move to the left, jumping at a distance of a every time. Now on this real line, 0 is somewhere. Let us say this is where 0 is. In that case, a will be here, at a distance of a from 0 to the right. So let us consider this interval, the interval from 0 to a. You start from B and start jumping at a distance of a, either to the left or to the right. In one of the directions, you would jump into this interval exactly once. That is, there will be exactly one point falling in this interval which is within this arithmetic progression. This interval has exactly one point of the AP. In particular, what we need to know is that there is one point. Suppose that one point corresponds to QR. Ordered pair QR corresponds to the one point that we find. Then at this point we have b minus qa equal to r, or b equals qa plus r. And here 0 less than or equal to r less than a. Now we have to argue that this ordered pair is unique. Suppose otherwise. Suppose q prime r prime is another such ordered pair. Clearly r prime is not equal to r, because otherwise q prime is the same as q, and therefore this ordered pair would not be distinct from the earlier one. So r prime is not equal to r, and r prime is b minus q prime a. That is because q prime r prime is an ordered pair which satisfies our requirement. So r prime is a non-negative member of the AP. That is because we assume that 0 less than or equal to r prime. Q prime r prime is another ordered pair where r prime is greater than or equal to 0. But then r is the least non-negative member of the AP. So r prime is greater than or equal to r plus a. But what is r plus a? This is b minus q a plus a. But this is then greater than or equal to a. And therefore r prime will not qualify, because we want a q prime r prime such that b is q prime a plus r prime and 0 less than or equal to r prime less than a. This is violated here. Therefore, there cannot be another ordered pair q prime r prime. So qr is unique. Hence our claim. If a does not divide b, then 0 less than r less than a. In that case, none of the points in the arithmetic progression will be divisors of a. Therefore, r will be strictly greater than 0. Now, it is easy to show this theorem for any two integers a and b, where a is not equal to 0. There exist unique integers q and r, such that b is q a plus r and 0 less than or equal to r less than mod a. See, here we only say that a is not equal to 0. We do not assume that a greater than or equal to 0. So you can prove this theorem yourself. We say that a is a common divisor of b and c if a divides b and a divides c, where a, b, c are all integers. So a pair of numbers b and c can have multiple common divisors. Every non-zero integer has only a finite number of divisors. Therefore, the common divisors of two numbers b and c, which are integers, form a finite set. Therefore, we can talk about the greatest of them. The greatest common divisor happens to be the largest of this finite set. So, we will denote this by GCD of B and C if B not equal to 0 or C not equal to 0. We can extend this notion to multiple integers. We can talk about GCD of BCD, which is the GCD of B and C and D, as we shall see. Now, we shall study an interesting theorem which says that if G is the GCD of two numbers B and C, then there exist integers x naught and y naught such that G is Bx naught plus Cy naught. In other words, if G is the GCD of B and C, then G can be expressed as a linear combination of B and C with integer coefficients. So, let us see how to do this. In particular, consider two numbers, let us say B equal to 3 and C equal to 7. Then we want to express the GCD of these two, which we know is 1. GCD of 3 and 7 is 1. We want to express 1 as a linear combination of 3 and 7. So, we could write this as 3x plus 7y. We have to find x and y so that 1 is equal to 3x plus 7y. That is precisely what the theorem says. The GCD of two numbers can be expressed as a linear combination of those two numbers with integer coefficients x and y. So, let us consider the various possible values of x and various possible values of y. When x equal to 0, y equal to 0, we have the linear combination evaluating to 0. When x is 1 and y is 0, we have 3. When x is 2, y is 0, we have 6. On the negative side, we have minus 3, minus 6. When y is 0 and x is 1, when x is 0 and y is 1, we have 7. When x is 0, y is 2, we have 14. On the other direction, we have minus 7 and minus 14. Here we have 10 and 17. This is how the values would look like. For various integral values of x and y, the linear combination 3x plus 7y would have these values. So, you find that indeed there is one particular choice of x and y for which the linear combination evaluates to 1. When x equal to minus 2 and y equal to 1, we have 3x plus 7y evaluating to minus 6 plus 7, which is 1. So, there is a choice of x and y for which the linear combination evaluates to 1. So, how do we generalize this? We want to make the assertion for every pair of integers b and c. So, we have this pair of integers b and c. Let us define the set S as the set of all integers bx plus cy, where x and y are integers. So, it is precisely this set that we depicted here for integers 3 and 7. So, this is clearly an infinite set. Let D be the least positive member of S. Depending on the various choices for x and y, we have different values in S. We are picking out the least positive member of S. We call it D. Say D is Bx naught plus Cy naught. Every member of S is a linear combination of B and C for some choice of x and y. So D is also the same. So there is a choice of x and y, namely x naught and y naught, for which D is Bx naught plus Cy naught. If D does not divide B, then there exist unique R and Q such that B is QD plus R. Where R is strictly between 0 and D. So we have R is B minus QD, which is B minus Q into Bx naught plus Cy naught. Rearranging, we get that this is B into 1 minus Qx naught minus C into Qy naught. Or I can put a plus here and move the negative sign here. So we have two integers, 1 minus Qx naught and minus Qy naught, so that R is a linear combination of B and C with these as the coefficients. But we know that R is strictly between 0 and D. Therefore, what we have found is that R belongs to S and R is positive. But we had picked D as the least positive member of S, and here we find R, which is positive, is a member of S but is less than D. Therefore, we have a contradiction. And from what did we derive this contradiction? We assumed that D does not divide B and then got this contradiction. Therefore, it must be that D divides B. Similarly, we can also argue that D divides C. So, if D divides B and D divides C, then D is a common divisor of B and C. Now consider the GCD of B and C. Let G be the GCD of B and C. Since D is Bx naught plus Cy naught, we have that G divides D, G divides B and G divides C. So, G divides Bx naught plus Cy naught as per the theorem we saw earlier. So, G divides D. G and D are both positive. So, since G divides D, G is less than or equal to D. But then G is the GCD of B and C, and D is a CD, a common divisor. G is the greatest common divisor. Therefore, clearly G is greater than or equal to D. In other words, G is equal to D. Or in other words, the GCD of B and C is the smallest positive integer that can be written as a linear combination of B and C with integer coefficients. Now, another theorem: for any two integers b and c, not both 0, the GCD is the positive common divisor that is a multiple of every common divisor. For any pair of integers b and c, not both 0, the greatest common divisor happens to be the positive common divisor that is a multiple of every common divisor. To prove this, suppose D is a common divisor of b and c, then D divides every linear combination of b and c. If D divides b and D divides c, then D divides bx plus cy for any pair of integers x and y. So, D divides every member of the set. In particular, D divides the least positive member of the set. This is what we call S. But then what is the least positive member of S? That happens to be the GCD of b and c. So, if D is a common divisor of b and c, then D divides G. So, every common divisor of b and c divides G. If G and G prime are both positive common divisors, that are divided by every common divisors, then G and G prime are themselves common divisors, then we have G divides G prime and G prime divides G, which implies that G equal to G prime. In other words, G is the only common divisor with this property, the only common divisor that is divided by every common divisor of b and c. In other words, the only common divisor of b and c which is divided by every common divisor of b and c is the GCD of b and c. Another theorem regarding GCDs: for every positive integer d, we have that GCD of BD CD equals GCD of BC multiplied by D. What is the GCD of BD and CD? This happens to be the least positive member of the set BDX plus CDY, where x and y are integers. Which is D times the least positive member of Bx plus Cy, where x and y are integers. This is the case when D is a positive integer, which is indeed the case here. But this is the GCD of B and C. That is precisely what we wanted to show. So, you can remove common factors from BD and CD. D is a common factor of BD and CD, and then find the GCD of the remnants. A related theorem is this: for every positive common divisor, TF, B and C, GCD of B by D, C by D is GCD of B and C divided by D. How do we prove this? In the previous theorem, you put DSD, B by D as B, and C by D as C. If you substitute thus in this theorem, we get the new theorem as a corollary. Yet another theorem: if GCD of A and D is 1 and GCD of B and D is 1, then GCD of AD and AB and D is 1 as well. In other words, look at the fraction A by D. You cannot reduce this fraction anymore. A and D do not cancel. Similarly, B and D also do not cancel. B and D do not have common factors other than 1. Therefore, if you consider AB by D, then D cannot cancel against AB. D and A do not have common factors, D and B do not have common factors other than 1. Therefore, D and AB also will not have common factors other than 1. Of course, intuitively clear to you, but how do you prove it? We know that GCD of A comma D equal to 1, GCD of B and D is also equal to 1. Therefore, we have integers x0, y0, x1, y1, so that one is ax0 plus by0 and one is bx1, sorry, d here, and dy1. So, there exist x0, y0, x1, y1, all integers, so that this is satisfied. Let us define z1 as d y0 y1 minus y0 minus y1 and z0 as x0 x1. If this is the case, then we readily find that AB into z0 is 1 minus dy0, 1 minus dy1. Replacing x0 and x1 with 1 minus dy0 and 1 minus dy1, we find that AB into z0 is this, which is 1 plus dz1. That is AB into z0 plus d into minus z1 equal to 1. Therefore, if you consider the linear combinations of A, B and D with integer coefficients, the least positive member of that set is going to be 1. If 1 is present in that set, certainly 1 has to be the least among them. In other words, GCD of A, B and D will have to be 1. That is it from this lecture. We will see more properties of GCDs in the next class. Hope to see you in the next. Thank you.